Ok, mesdames et messieurs, bonjour. Bienvenue au Collège de France. C'est avec un grand plaisir que je vais présenter plusieurs personnes qui sont les grands chercheurs et chercheuses du domaine de l'algorithmique répartie, en commençant par le professeur Nir Shavit à l'Université Tel Aviv et au MIT, et qui est aussi à la tête d'une start-up Neural Magic. Et ils vont tous, je pense, parler français, peut-être à l'exception de Michel, ou peut-être même tous. Voilà.
I speak in here. Yeah, right. Hi, everybody. I don't have that much time, so I'm going to try to kind of talk to you about more about the problem that I'm trying to solve than the actual mathematical computer science solutions. So as you can see from the title, I'm going to talk about high throughput connectomics. And for many of you, maybe the name connectomics doesn't mean much, so I kind of want to show you a little bit about it and what it means. If I can get this to move forward, that would be good. Yeah. So here it is, the Cray 1 supercomputer, maybe the first supercomputer built by humans. And, you know, this is a picture of Mount Fuji. And it takes you probably 1/10 of a second to recognize Mount Fuji. Okay, and how do you do that? Well, you use, neural circuitry to do it. What is this neural circuitry? So just at a very high level, right? We have in our heads, billions of neurons. Each one of these is a cell, right, that essentially has connections called synapses. And connections called synapses on kind of the input and the output of it. And it collects in a part of the neuron called the dendrite. It collects signals from these synapses, adds them up, kind of sees if the collection passes some threshold, and if so, sends a signal down the axon, which again sends signals through synapses to other neurons. And so this kind of circuitry, right, of axons connecting to dendrites, connecting to axons, connecting to dendrites is what is going on, right, in our heads. The connections themselves, right, are chemical. They're kind of slow, okay? We're essentially exchanging chemicals over these little boundaries, and that way we are actually managing to kind of pass this signal across. Now, our brain itself, okay, consists of white matter and gray matter. The gray matter being kind of the cells, the bodies of the neurons, right? And a lot of kind of connections. And the white matter are axons going across our brain from one side to the next, okay? And it's called white matter because it's covered with this kind of myelin, this coating, that makes it look white. So if you will, just as in the same way that the Cray supercomputer has a whole bunch of processors, okay, on the outer side, and a lot of wiring in the middle, this is the same kind of thing that happens in our brain. It's essentially this real supercomputer. And in 1/10 of a second, okay, this supercomputer that we have in our heads recognizes Mount Fuji. So 1/10 of a second, okay, in terms of these neurons chemically firing from one to the other, is about 20 neurons firing in sequence. 20 neurons firing in sequence, okay, think of it, and I'm recognizing, this complex picture and understanding that that actually is Mount Fuji. So there's an incredible amount of parallelism here. And this parallelism is the thing that drew me to this field because, working on parallel and distributed computing for many, many years, it kind of came to the realization that the way we were doing things right now is not going to carry us to the next level, in terms of the ability to parallelize things. And so I thought to myself, okay, it's a great idea. Let's look at the brain, this massive parallel computer, and try to understand, how the brain does it. So this is my goal, okay? This is the goal of my research. Now, so how do you go about, right, understanding this parallelism? Well, this brings us to the graph of the brain, okay? A brain graph, we call it a connectome, okay? And if you look at a fly, okay, the fly's connectome, there are about 100,000 neurons in the fly's brain, 100 synapses, okay, connect from each neuron, so about 10 million edges in this graph. A mouse's cortex, okay, just the cortex part of the mouse, 4 million neurons, 10,000 synapses for each, so a graph that's got 40 billion edges. The human cortex, 30 billion neurons, okay, 10,000 synapses, so 300 trillion edges. Okay, that's a huge graph. Okay, so how do you go about understanding such a thing? Well, the attempts that we're making right now, okay, which we were never able to do before, is to actually try to use electron microscopy, okay, to take little slivers of brain, okay, and slice them up, photograph them with an electron microscope, see the synapses, see it on synaptic level, and then see what the graph looks like. Okay, so the process of doing this is essentially as follows. So you take a piece of brain, mouse brain, let's say, you kind of put it in a resin, okay, and then you take a piece of it, slice it up with what's called a microtome, image it, okay? Then, once you have these images, you have a stack of images, you align them, and then you do a process of reconstruction, okay? And this process of reconstruction is done using machine learning algorithms. And finally, we can visualize and look at what we see. So, this is an example of what a microtome looks like. Okay, this is a device that takes these little slivers and actually, takes something that might be even just a cubic millimeter, like a grain of salt, and dices it up. You know, you could cut a cubic millimeter could be cut like 30,000 times with this device. And the way it works is, if you look at it in detail, it has this bed of water, okay, and it has the microtome knife going up and down, and the piece of let's see if I can make this. Right here is a piece of mouse brain, and it goes up and down on this edge. There's a diamond knife here. The slivers get cut and put onto this tape. And so what you get is essentially a brain on tape, okay? Many, many little pieces of brain all put on this tape. So here's an example of, 10,000 little slices like this. Okay, and if we take them all together and we reconstruct them, what we would get, right, is essentially a reconstruction of a block of brain. This is about 100 terabytes worth of imagery of a piece of the thalamus of a mouse. This is what it is. If this is a penny, that's the size of this thing. Okay, so it's really tiny. Now, a few years ago, the problem with doing this was mainly the problem of how to collect the data, right? How to actually take that little sliver and cut it up and do the process of imaging all those slices. But we've learned how to do that really well now, okay? So we can do the actual collecting of the data really fast. This is a picture of my colleague from Harvard, Jeff Lichtman. This photo shows you how small Jeff is. And what you see here is the Multisem microscope. It's a microscope that has 61 parallel beams. So in parallel, it actually takes, huge high-speed imagery of these little slices, and it can produce data at about 0.5 terabyte an hour. So now suddenly the bottleneck, okay, for actually doing machine learning has changed from being the collection to being the processing, the machine learning to do the reconstruction. Okay? So just to understand, this is what we call a big data problem. It's a really big data problem. Okay, so if you look at the, again, how is this done here? No, yeah. If you look at a cubic millimeter, that's about the size of the Walmart database, about 2 petabytes in terms of data size, right? If we were to do, the brain of a rodent, that would be an exabyte, okay? And the human would be a zettabyte. So basically, this is our first goal, okay? We want to do a cubic millimeter. And that's already on the way. We're, managing. It's taken about 10 years to get to the place where we can actually do a cubic millimeter, okay? And our next goal will be to do a rodent. This is going to be a huge project, hundreds of millions of dollars in expense to do something that is similar to the, to the Genome Project. We are going to try to take a mouse brain and actually segment it fully. Now, what are we going to get if we actually manage to do that? Well, here's an example of a slice through a mouse brain, okay? And what the process that we want to do, right, is to take this mouse brain and with machine learning algorithms manage to kind of mark up, the various elements. Now, we want to do this with machines because to do this, okay, this is an example of how we do it, how humans do this, how they mark it up, okay? And the problem is that the human reconstruction is very, very slow. So to do large volumes, to do, essentially the exabyte of a mouse brain, we're going to have automated ways of doing this. But if we could do it, okay, then here's what we would get. Here's an example of a reconstruction, okay, of 2 slivers of, kind of a, of 2 dendrites in a mouse's brain. And so this is the red dendrite, the green one, and all these little bumps that you see here, okay, are going to be kind of connected to are going to be synapses to other axons. So let's look at one of these as we look at what surrounds them. So you can see here in the same volume, okay, these are all the other dendrites surrounding those 2 dendrites, okay? And these are all the axons surrounding those 2 dendrites, okay? And these are all the glia cells, the kind of support cells surrounding them. So together, this tiny little volume, okay, is extremely dense. And we want to automatically go and reconstruct all of this structure and the connections between them to kind of get the graph. Now, as I said, the human reconstruction takes too much time, okay? And so what we want are automated techniques for doing this. And so, unfortunately, I don't have enough time in this talk to actually show you the history of how this field has progressed from doing, almost nothing in size and being really inaccurate to automated techniques that now manage to track neurons in tissue as good as humans, but I want to show you a little bit of this technology. So I'm going to show you one algorithm. This is an algorithm by my postdoctoral researcher, Yaron Meirovich, and it's a technique called mask extend. And what it does is it uses a machine learning algorithm, okay? It takes a kind of, when we are going through the EM stack, it predicts membranes in this image, what is a membrane and what isn't. It takes the prior location where we think the neuron was, and it projects where the membranes will be and where the new neuron is, and it's trying to kind of do what people do when they go through these image stacks, which is kind of mark them, and we are really, really good at actually figuring out which continuation in the imagery belongs to a given neuron. Okay? So we want to mimic that with a machine. Okay? And this algorithm is running essentially on a traditional Intel multi-core machine. Okay? And it basically runs the algorithm, goes through the image stack. And let me show you an example of its execution. So what I'm going to show you now is this algorithm, MASIS10, running through a kind of an image stack, from a mouse brain. The green part is where the machine learning algorithm is focused, and the red are the membranes, and this blue piece is the actual axon that we're tracking. Okay. So as you can see, what's going on is we're going in through slice after slice after slice, and the algorithm is kind of following this little sliver of brain, okay, as it goes through. And until very recently, it was basically impossible to do this without losing track of it. But now we have the kind of technology for doing this.
Why is it moving?
What?
Why is it moving?
From slice to slice.
Oh, it's slices.
Yeah, this is
It's
slice.
not really moving. It's moving slowly.
It's not really moving. This is slice after slice after slice. He wants to understand. What do you want? It's okay. And I just want to show you, compared to traditional techniques, so what I'm going to show you here is, this is an example of using a traditional way of doing this, okay? What I mean is prior pipeline techniques. This is how a human that does it, okay? Here is our algorithm, and this is the actual data set. So let me show you this. So what you can see is the algorithm follows this, but if you look now at the traditional pipeline, you'll see that while the human and the new algorithm are managing to continuously follow, here there's going to be, right now it's green, okay, and there's going to be a change of color because the algorithm kind of loses track of this neuron and thinks that it's a different neuron. So it's still green here, okay, it's getting, changed color because it doesn't realize it's the same one, okay? And so the algorithm that we invented here is essentially a way of overcoming that problem and managing to track it through without losing the neuron itself on the way. And you can use this technique, okay, to do multiple, reconstructions like that, and it can get, and it can get really dense, okay. Again and again, running through and tracking. There are, even a little sliver of brain, there could be hundreds of thousands of these going through. And so just doing this kind of tracking one after the other, is kind of wasteful and not that accurate. And so in my lab, my postdoc Yaron and my student Lu Mei actually invented a technique of doing all the neurons, tracking all of them through the image stack together in a very efficient way. Unfortunately, I don't have time to describe this algorithm, but I just want you to kind of get a feel of what it might look like if we did all of them at once. So here's an example of this kind of a tracking, okay, where we're at the same time going through the slices and detecting all of the neurons at the same time. So, unfortunately, I'm out of time in a minute, and so I'll just say a few words about this. So, okay, so you're asking yourself, oh, great, Nir, so you've got all these graphs, and, and now what? What's the next step? Okay, and so my answer to this is as follows. What we're doing here, right, is essentially collecting data. And in the same way that Galileo, didn't know what he would find when he pointed his telescope at the sky, we are actually pointing our, connectomics machinery at the brain and trying to collect these graphs and this information, okay? And we don't know exactly what we will find. Would we believe, right, that by looking, right, we are going to actually find out new things that we didn't know before. Okay, so that's the hope. And thank you very much.